Let's take a look at an integration by parts problem and see if we can have some fun with complex numbers, because I know that's the top on our minds these days, right? So here's e to the at times sine bt dt. And remember, if we do integration by parts on this, we have to do integration by parts twice, and we end up with a loop, and we have to break out of the loop. So let's do something else instead. You might not have seen this before, or maybe you have. That cosine x can also be written e to the ix plus e to the minus ix over 2. And that's cosine. How about sine? Sine x can be written e to the ix minus e to the minus ix. So very similar except a minus here. And then divided by 2I, so it's a little bit different. But let's use that because that'll turn things into e's, powers of e, and powers of e are fairly straightforward to integrate. So let's write this sine x here, but instead of x, we'll have bt, right? So we'll have integral e to the at times, I'll write the 1 over 2i here to give myself some room. So it'll be e to the ix, but x is bt, minus e to the minus I bt dt. Let's move out the 1 over 2i and distribute the e to the at. So 1 over 2i is a constant. I'll take the integral and then distribute the e to the at. So we have e to the at, e to the ibt, minus e to the at, e to the negative ibt. And now let's combine this. Remember something like e to the x times e to the y is e to the x plus y. That's true for real numbers. It's true for complex numbers. It turns out it's not true for matrices, which is a really interesting story. But we don't have matrices here. So we'll copy that and we'll say e to the at plus ibt minus e to the at minus ibt dt. And now we have a t in both parts of this exponent and a t in both parts of that exponent. We can gather like terms. So we'll have 1 over 2i integral e to the a plus ib times t minus e to the a minus ib times t dt. All right, so now I just have e to a constant times t and e to another constant times t. We know that the integral of e to the, let's call it kt, is 1 over k e to the kt, right? We know that for real numbers, for k as a real constant, but is the same true for complex numbers? On one hand, I could just tell you it turns out it is. On the other hand, we could just try it and see if we get something sensible. So either way, we're going to go straight forward. So I'm not going to write the integral sign now because I'm taking the antiderivative. What's the integral of e to the a plus ib times t? It would be 1 over a plus ib e to the a plus ib t minus, and then the same thing here, but my constant as a minus ib, e to the a minus ib t plus c, because we're done taking the antiderivative. So in some sense, we could just stop here. We have taken an antiderivative. It turns out if you plug in stuff, all the complex numbers will cancel and you'll get real numbers. So we could stop here. All the calculus is done. But you might say, well, I originally had something in terms of sine. It might be nice to have it back in terms of sine again. So we could simplify. How are we going to simplify? Well, I've got fractions here, and it might be nice to add those fractions. And not just the fractions, but the e to the power too. If I have a fraction of with a denominator of that and a fraction with a denominator of that, what's my common denominator? it would be 1 over a plus ib, a minus ib. So I need to multiply this term by a minus ib over a minus ib, multiply this term by a plus ib over a plus ib, and then add them. So we'll get 1 over 2i, and we can write the common denominator out here, a plus ib, a minus ib. And then this term, so my denominator's out here, so everything in the big parentheses will be the numerator now. And this term will have an a minus ib on it, e to the a plus ib t minus, and then this will have an a plus ib, e to the a minus ib t. All right, and then we can expand these terms, like multiply the e to the stuff times the a, e to the stuff times the ib, and we'll have an e to the at here and an e to the at here, so we'll factor that out too. So we'll have 1 over 2i times this, a plus ib, a minus ib, e to the at times, and we'll gather the a times this and the a times that, so we'll have a times e to the ibt minus e to the minus ibt, and then we'll have minus ib times e to the ibt minus e to the minus ibt. Whoops, I've got to look at my minuses here. I have a minus ibt and a minus ibt, so I actually have two ibt's that are each positive if I've got the negative out there. Let's look at this term. It's a squared, and then a times minus ib, and then ib times a. So those terms cancel each other out, and then I have an ib times a minus ib. So I have a minus ib squared e to the at. Let's bring this 1 over 2i in. We'll have e to the ibt minus e to the minus ibt divided by 2i, and we'll have minus ib over 2i e to the ibt plus e to the minus ibt, like that. And now let's simplify. This is a squared. If I square the I get minus 1 b squared e to the at, and then a times, and then what is this? E to the ibt minus e to the minus ibt over 2i. That's sine of bt. And then here the i's cancel. I get a minus b, and e to the ibt plus e to the minus ibt divided by 2, that's cosine of bt. And over here I can simplify the minus 1 times b squared to just get 1 over a squared plus b squared e to the at times this whole thing again. No simplifying there, which that has a Pythagorean theorem kind of feel to it, doesn't it? Isn't that interesting? So at this point, all the i's are gone. We're just back in terms of real numbers. And we did this interesting integration by parts problem. Did you notice we never actually did an integration by parts on it? We didn't do a u and a v and stuff. Just by turning it into sines and turning sines and cosines into complex numbers, in some sense we solved a more general problem, or a problem in a kind of bigger space, and then re-specialized it again to just the real numbers. So you could almost say, and often we do say, that what's really going on in this problem is all the complex stuff, and e to the at sine bt is just kind of a diminished view of it. If you want some fun, you can go check that by taking the derivative. Maybe I'll do that in the, type that out in the YouTube description or something.